Welcome to section 4.3, where we connect f prime and f double prime with the graph of f. There are a lot of ideas in this section, and the first one that we're going to look at is the relationship between a function's first derivative f prime and the original function with the first derivative test. We've already talked about the first derivative test, and we know that it's used to find relative extrema, the local or relative minimum and maximum points. Now, we can also use the first derivative test to find the intervals of increase and decrease of a function. In order to do that, we have to make a good sign chart, and the sign chart depends on the critical points. If you do not remember critical points, I recommend that you look back at the video called Finding Critical Points. The first derivative test definitely highlights the relationship between a function and its derivative, and it helps us to analyze the original function using the first derivative. Before we delve more into the first derivative test, it is important that we recall the relationship between a function and its first derivative, f and f prime. The main idea behind this relationship is that when a function is increasing, that means that the first derivative is positive. When a function is decreasing, that means that f prime is negative. When a function is neither increasing nor decreasing, that means that f prime equals 0. So what I've done is marked up this original pink f graph, f of x, into where the first derivative is negative, meaning when our function's decreasing here and here, from negative infinity to negative 3, and also from 4 to infinity. And then also where f prime's positive, which is where our original function is increasing, from negative 3 to 1, and then again from 1 to 4. We can't just say from negative 3 until 4, because right here we actually have like a little like sort of squiggle, meaning our function is neither increasing nor decreasing here. It levels off just for an instant, and therefore our derivative is 0 here. If we were to draw a tangent line, it would be horizontal. Same with here and here. So as you can see, just because a function's derivative equals 0 does not necessarily mean that there's a relative extrema there. Here, of course, is a minimum, and here, of course, is a maximum, both relative because we go to infinity and negative infinity, and therefore there are no absolute extrema, but again, still extrema. Here, just because the first derivative is 0 doesn't necessarily mean that there is a relative min or max. It simply means that the slope of the tangent line would be 0. So how can we tell whether or not we're going to have a relative extrema? Do we have to graph? No. So the reason that we find critical points is that the derivative equals 0 or is undefined. And so we'd have 3 critical points here. X is negative 3, x is 1, and x is 4. In order to tell if a critical point is also a place where relative extrema occurs, we have to not only know that the first derivative is 0, but we have to note if there's a change in the sign of the first derivative. Meaning, does our first derivative change from negative to positive or positive to negative? If it does, then we have a relative extrema. So note here at x is negative 3, our first derivative went from negative to positive, meaning our function decreased then increased. Therefore, there was a relative min. Here at x is 4, our first derivative went from positive to negative, meaning our function increased then decreased. Thus, there was a relative maximum point. However, at x equals 1, even though we had a critical point and our first derivative was 0, our first derivative did not change sign. It was positive and then positive again on either side of x equals 1. Therefore, since our first derivative did not change sign, we did not have a relative extrema occurring there. And we can do this with a sign chart to analyze rather than having to look at the graph of a function every single time. That's what we'll explore in these next 3 examples. Here we want to use the first derivative test to find the relative extrema and also the intervals of increase and decrease on our function f of x. Our function f of x is a cubic trinomial. The first step in order to use the first derivative test is to find the critical points. Again, if critical points are something that you need to review, I recommend going back to the video about critical points. In order to find a critical point, what we have to do is find the first derivative of our function. Simply using the power rule, our first derivative is 3x squared minus 12. In order to find the critical points, we want to find where our first derivative is 0 and or where our first derivative is undefined. Since our derivative here, f prime, is a polynomial, it's specifically a quadratic binomial, it is continuous and differentiable everywhere, it is defined everywhere, so we're not going to have to worry about where it's undefined. So we only need to know where it equals 0, and there's two different ways that we could solve this. I am actually going to get into the mode of factoring because that is how normally you do want to solve these. So we got it equal to 0, we set each factor equal to 0, that does not provide us with any solutions. And then x squared minus 4, you could add 4 and take the square root, or again we could factor and set each factor to 0 because sometimes it's easy to miss that plus or minus sign. So we do actually end up having two critical points. They are -2 and 2. And so these are our critical points. So once we found the critical points, the next thing that we need to do is make a sign chart using those critical points. A sign chart is important because it'll tell us the sign, SIGN sign, of our first derivative in the intervals created using those critical points. So our next step is to make a sign chart. And I believe that before I did refer to the sign chart as a number line, I should have definitely referred to it as a sign chart. So the sign chart looks like this. It does look like a number line, which is why I called it one. And we want to put f prime above and x below, telling us like what we're dealing with on either side of this. So down here we care about our critical points, -2 and 2. And up here, we're looking for like what the output is of f prime when we plug in these certain values. Well, we know that when we plug in -2 or +2 into our first derivative, f prime, that we get 0 out. I mean, that's what we solved for. We set it to 0 and got -2 and 2. So our outputs here are 0. So I'm just going to put little zeros there above it. What we really care about, though, is the sign. We care about what f prime is in this interval to the left of -2, in this interval in between -2 and 2, and in this interval greater than 2. We care about that because we care about the sign of f prime. If f prime is positive, that means our original function was increasing. If f prime is negative, that means that's where our original function is decreasing. And if we have a change in the sign of f prime, that means that we have either a relative minimum or a relative maximum, depending on if we go from negative to positive or positive to negative. So let's plug in a couple points. We want to plug them into f prime, and I want to plug in a point first to the left of -2. So we can just think, let's plug in -10, something that's very far to the left here. What I'm actually going to do is refactor this off to the side so it's easier to work with. So this is really 3, and then it was x squared minus 4, so it was x plus 2, x minus 2. I always think that it's easier to use something that's factored rather than something that's not factored, but it's completely up to you. You can plug it in here or here. It does not matter. So I'm going to plug in -10, and again, I don't care really what the number is that I get out. I care about if it's positive or negative, so we can be pretty general. So if we plug -10, you can't plug anything into 3. This 3 does nothing. So we plug in -10 here, we'll get a negative inside this factor, and we'll get a negative in this factor. A negative times a negative gives us an output of positive. Now let's say you didn't plug it into the factored form that I had in orange. You plugged it into the non-factored form of yellow. You'd have 3 times -10 squared. That's 100 times 3. That's 300 minus 12. That's a huge positive number. So either way, you get a positive output. Then we want to plug in a number in this interval in between a negative and positive number. I like to just plug in 0. It makes life easy peasy. So if we plug in 0, 3 is always positive. We'll have a positive number here and a negative number here. So a positive times a negative is a negative. So we have a negative in between here. Again, if you plugged 0 in here, you'd have -12. Negative number. Then plug in a positive number here. I'm just going to plug in +10. We'll have positive and positive in here to get a positive output. So what does this mean? This means that our original function increased, and then at -2 it began to decrease, and then once again at 2 it increased again. So our function, if we wanted to sketch it, our original function f increases, and then at -2 it decreases, and then at 2 it increases again. So it looks something like that. That means that since our function went from increasing to decreasing, the first derivative was from positive to negative here at x is -2, that means x equals -2, a relative maximum occurs there. And then for those same reasons, just in like the opposite direction, since our derivative is negative and changes to positive at x equals 2, meaning our original function decreased and increased, that means a relative minimum occurred down at x equals 2. So our conclusions look like this. We have a relative max occurring at x equals -2, and we have a relative minimum occurring at x equals 2. Now I put this here because we could find what those actual maximum and minimum values are. All we have to do is plug in to our original function. So let's do that real quick. Let's plug in -2. When we find f of -2, we'll have -8 plus 24, so -8 plus 24 is 16, minus 5 is 11, doing some real-time mental math here. Then our relative minimum, plugging in 2 to our original function, we'll have 8 minus 24, so -16, cool, minus 5 more is -21. So we know where these relative extrema occur using our first derivative test, the sign chart. But in order to find what they actually are, the y values, we need to just do some old school math and plug it into our function. Now the very last thing that we need to do, we just found the relative extrema, that's like in green. We want to find the intervals of increase and decrease, and the way that we can do that is using the conclusions from our sign chart here. So I sketched the graph of f because it just correlates so well with its derivative. And so our intervals of increase are where our first derivative is positive. So our interval of increase is from -infinity to -2. And also our first derivative is positive from 2 to infinity. So that's where our function's increasing. And then f of x is decreasing when the first derivative is negative, so in between -2 and 2. So we have found, using the first derivative test, our relative extrema and also the intervals of increase and decrease. Here's another example that is the same set of directions. So again, we want to use the first derivative test, which gives us the relative extrema as well as intervals of increase and decrease. So in order to use the first derivative test, again, our first step is to find the critical points. Critical points are where our first derivative, g prime in this case, is 0 or undefined. Now, g here is a product, so we actually need to use the product rule. So we'll let u be x squared minus 3, and v will be e to the x. Then u prime, using the power rule, is just 2x, and v prime is the same as v, e to the x. So we'll do u times v prime, so we'll have x squared minus 3 times e to the x plus v times u prime, so 2x e to the x. Then, when we set something to 0, what we want to do is factor it. So what we can do is pull out the greatest common factor, which in this case it looks like is just going to be an e to the x. So we'll be left with an x squared minus 3 over here and a plus 2x over here. So we now have a quadratic trinomial. We have x squared plus 2x minus 3, and that actually is factorable. So factoring it, two numbers that multiply to -3 that add to 2 are x plus 3 and x minus 1. So now we have 3 factors, and we can set each one of them to 0. So we'll set e to the x to 0, we'll set x plus 3 to 0, and we'll set x minus 1 to 0. This is never going to be undefined. First of all, this right here, this factor, you can look at it broken up as well, but it's just a polynomial, and so it's defined everywhere. E to the x is also defined everywhere. It's an exponential function, and so its domain is all real numbers. We can plug in any number we want. However, setting it to 0 does pose kind of a problem because no matter what we raise e to, remember e is about 2.7, whatever we raise it to, negative, 0, or positive, we always get an output of positive. Therefore, e to the x or any number to the x really is not going to give us 0. So this does not give us any solutions. Then the other two solutions are easy enough. We'll have x equals negative 3 and x equals positive 1. So our two critical points are x equals negative 3 and x equals 1. Our next step is to use those critical points to make a sign chart. The sign chart is going to tell us where our function's increasing and decreasing by telling us the sign of our derivative. So what I did is left the first derivative in factored form because it's much easier to plug into when it's in factored form. So our sign chart looks like a number line. We have x values down here and then g prime values up top. We want to put our critical points on here and then their outputs up top. When we plug in negative 3 or 1 into our g prime, we get 0 out. Now we care about numbers to the left of negative 3 in this middle interval here between negative 3 and 1, as well as numbers greater than 1. So again, we only care about the sign. We don't necessarily care about the number. Now e to the x, no matter what you plug in here, just as a quick reminder to make it simpler, e to the anything is always a positive output, no matter what. So we don't really care about plugging in a number into e to the x. We don't need to worry about that. We just care about the things that can change sign. So if we plug in a number less than negative 3, let's say plugging in negative 10, we'll have a negative inside here and a negative inside here, which will output a positive when we multiply. Then we can plug in 0 because 0 is an easy thing to plug in between the two. E to the 0, again, just 1. It's always going to output something positive no matter what you plug in here. Then 0 plus 3 is positive, and 0 minus 1 is negative. So we'll have a positive times a negative here, which is negative. Then to the right of 1, if we plug in a number greater than 1, like 4, we'll have a positive and a positive. So that's a positive outcome. So our sign chart is telling us where our derivative is positive or negative, which tells us where our relative extrema are, as well as where there's increasing and decreasing. We can make the following conclusions. Because our first derivative changes sign at negative 3, negative 3 is a place where a relative extreme occurs. Because the first derivative goes from positive to negative, that means we have a relative maximum at x equals negative 3. In order to find what that relative maximum value is, you can plug negative 3 back into this original function. So it looks like we'll have 9 minus 3, or 6, times e to the negative 3. So it's 6 over e cubed. Next, our first derivative also changes sign at x equals 1. That means at x equals 1, there's also another relative extrema occurring. Because our first derivative goes now from negative to positive, that means there is a relative min at x equals 1. Plugging 1 back into our original function can give us what that actual value is. So it looks like we'll have 1 minus 3, so negative 2 times e, or negative 2e. Lastly, our function is increasing and decreasing wherever the first or negative, respectively. So g of x, our original function, increases where the first derivative is positive. So our original function's increasing from negative infinity to negative 3, and also from 1 to infinity. Our original function g is decreasing where g prime is negative, which is from negative 3 to 1. In our last example, we have a particle moving along the x-axis, so it's moving either left or right with a given position function here. And of course, for t is greater than or equal to 0, since t is time. We want to first find the velocity function and then describe the motion of the particle. So this is really just using the first derivative test. If we think about what the first derivative is, it's the velocity, and velocity is speed and direction. So if the velocity is positive, that means the particle is moving to the right. And if the velocity is negative, that means the particle is moving to the left. If the velocity is 0, that means the particle has stopped or paused. And that either means a change in direction or it just means an actual pause in speed. So let's first find the velocity function, which is the first derivative, x prime, and we will simply use the power rule here. So we'll have 6t squared minus 28t plus 22. Then we want to find the critical points by setting this velocity to 0, and it looks like we can factor out a 2. So we'll have 3t squared minus 14t plus 11. Factoring this inside quadratic here, we want two numbers that are going to multiply to 3 times 11, or 33. That will add up to negative 14, our b value. Those numbers happen to be negative 3 and negative 11. So factoring this, we'll have 3t squared minus 3t minus 11t plus 11. And then we factor this by grouping. So we'll have 3t, t minus 1, and then minus 11, and then t minus 1. Now, I don't like this outside parentheses here. It's like unnecessarily confusing. So I'm going to change this to a bracket instead, because that 2 is still out front. All right, so from here, we'll have 3t minus 11 is one factor, and then t minus 1 is our other factor. Yes, we still have the 2 out in front, but it really is not doing anything in terms of the first derivative test, because it's not going to like provide us with a critical point or change anything. So when we find our critical points here by setting each one to 0, it looks like we'll get t equals 11/3 and t equals 1. Those are the critical points. That's where the velocity is 0 of the particle. So we have our critical points. The next thing we need to do is make a sign chart. The sign chart will have t, and our t values are 1 and 11/3. And you can either put the first derivative of position up here, or you can just write velocity, which is what the derivative of position is. And then we know that when we plug in 1 or 11/3, our velocity is 0. However, we want to know what the velocity is in each one of these 3 intervals. And so we can plug into this function right here, or this velocity function here. It's completely up to you where you plug it in. I personally like plugging it into the factored form. I think that's easier. So this is, again, just the other way of writing v of t. It's just the factored form, whereas up here it's not factored. So if we plug in a number less than 1, let's plug in 0. 2 is always positive, it's not changing anything. If we plug in a 0 here for t, we'll have a negative number in here, and then 0 here we'll have another negative number. So we'll have positive output here. Then if we plug in a number in between 1 and 11/3, let's say 2, when we plug in 2 here, we'll have a negative, but if we plug in a 2 here, we'll have a positive, and a negative times a positive is a negative. Then, to the right of 11/3, we can plug in a number like 10, which is much larger than 11/3, so it's going to be positive and positive again, and a positive times a positive is a positive, so that is our sign chart. Then we've already found the velocity function, it's right here. But now we want to describe the motion of the particle. So describing the motion of the particle means sort of like what increasing and decreasing meant in the other functions. When the velocity is positive, that means our position function is increasing. Well, on an x-axis, you can only go 2 directions, left and right. If it was a y-axis, it'd be up and down. And to the right means positive because the numbers on the x-axis are increasing. So because the position function's increasing here, because the velocity is positive, that means our particle is moving to the right. And it means it's moving to the right here. In between time is 1 and 11/3. Our velocity is negative, meaning the position function is decreasing, aka the particle is moving to the left. We can come to the following conclusion about the particle. I actually don't really mean to have this to the left arrow here because t does have to be greater than or equal to 0. It really does depend right here if you want to put like a less than or equal to sign here, because some people might argue that you can't really be, I don't know, moving at like the very first instant. So that's up to you how you want to say that right here. But basically, until the first second, our particle is moving right. And also after the 11th third of a second, our particle is also moving to the right. And then in between 1 and 11 thirds for time, our particle is moving to the left. To conclude our video here about the first derivative test, I wanted to show a quick example without even a function here, just a more abstract example about sometimes that we don't have both types of relative extrema. So if we take a look, let's say we had some function and we found that the critical points were -3, 1, and 4, and we have the following sign chart. 1 made our denominator 0, so it made the first derivative undefined, and then -3 and 4 made like the numerator 0, just made our first derivative 0. Let's say we only change signs one time. Well, that means we can have only one relative extrema. That's okay. Um, Even though x equals 1 and x equals 4 are critical points, that doesn't necessarily mean that they're relative extrema. What means that's relative extrema is occurring is when the first derivative changes sign. So because our first derivative changes sign at x equals -3, and it changes from negative to positive, we say that there is a relative minimum at x equals -3. We do not have any relative maximum points because the first derivative never changes from positive to negative. This function is always increasing after this point, so there is never any relative maximum. So I just wanted to throw that last example in there since we didn't have any that showed sort of these anomalies. Best of luck.